Introduction to chemical change and rates of reactions. Chemical change focuses on the relationships and laws that govern chemical reactions. We will answer questions such as, how can we predict if a reaction will take place? How fast will a reaction proceed? And how far will a reaction go before it stops? In certain reactions, almost all the reactants are converted to products. In other reactions, the products break up again to reform the original chemicals. The rates at which chemical reactants are converted into products vary widely. The combustion of petrol in a car engine is explosively fast. It seems to be over as soon as the reactants make contact, in a fraction of a second. Cooking, or rusting of iron, however, takes a moderate length of time, from minutes to months. Still others take much longer. The reactions that make up the human aging process continue for decades. The formation of coal from dead plants takes hundreds of millions of years. Knowing how fast a chemical change occurs is essential. How quickly medicine acts in the blood system can make a difference between life and death. We're also required to understand the time taken for cement to harden, polyethylene to form. Textile industries put emphasis on how long to dye certain types of fabric to ensure financial profit. In general, the rates of these diverse processes depend on the same variables, most of which, within a given time, can be manipulated to maximize outputs. In chemistry, we call these yields. When they slow down, they're called unwanted reaction. Reaction rate is the central focus of what we call chemical kinetics. Chemical kinetics is an area of chemistry in which we study the speeds or rates at which chemical reactions take place. It shows the change in the concentration of a reactant or a product with time. The rate of reaction. From earlier studies, you know that a reaction can be represented as reactants, forward arrow, products. The arrow implies that during the reaction, reactants are used up and products are formed. During the course of the reaction, the concentration of the reactants will decrease and the concentration of the products will increase. We measure the change in concentration to determine the rate or speed of the reaction. Rate of reaction equals to change in reactant concentration over time period, which is the same as change in product concentration over time period. The rate of reaction can also be represented graphically as a decrease in the reactant molecules with time, or as the increase of the product molecules with time. Collision theory. It is quite evident that if you have a situation involving two species, such as particles, for example atoms, molecules or ions, they can only react together if they come into contact with each other. They first have to collide, only then may they react. Why do we state may react? It isn't enough for the two species to collide. They have to collide the right way around and with enough energy for bonds to break. In chemistry, this is what we refer to as the orientation of collision and the energy of collision. We will not be focusing on the details of orientation just yet, so let's look into energy collision. Energy of collisions. At higher temperatures, the particles have more energy and the collisions are more energetic. When the particles collide, what happens first is that they form an activated complex. This is just an intermediate, short-lived group of atoms before they form the product. This is where old bonds are broken and new ones are formed. At the pivot of the activation complex, we have activation energy with a symbol EA. This is the minimum amount of energy required to bring about a chemical reaction. When the particles collide, they must have combined energy greater than this activation energy, otherwise they will not react. Reactions go through this process in different steps. Some consist of one step only, like the neutralization reaction between sodium hydroxide and hydrochloric acid to form sodium chloride. Many others, however, involve more than one step, with each step having its own reaction rate. The overall reaction is determined by the slowest step, which is called the rate-determining step. The study of processes is called reaction mechanisms. Collision frequency. To affect the reaction rate, which is what we are interested in, the processes of having enough collision energy and proper orientation has to happen often. We call this frequency of collision. The frequency of collisions is determined by the concentration and the temperature. Concentration. When the reactants are more concentrated, basically the more squeezed the molecules are, more collisions will occur because there are more particles that can collide in a given volume. Temperature. At higher temperatures, the particles have more energy and move faster, hence they bump into each other more often, increasing frequency of collisions. The Boltzmann distribution. Due to the key role of activation energy in deciding whether a collision will result in a reaction, it would be useful to know what proportion of the particles present have energies high enough to react when they collide. In any system, the particles present will have a very wide range of energies. In a gaseous mixture, the energy of individual molecules varies enormously, but must have an average speed. The Boltzmann distribution represents the number of particles with specific energies. The area under the graph represents the total number of molecules. Note, this number does not change as the temperature changes, only the distribution of the particles. So when temperature increases, the average speed of the particles also increases, giving more particles enough energy to react. For example, in this graph, the number of molecules with enough energy to react is small. If we increase the temperature, the number of molecules with enough energy to react also increases. Looking back, we emphasize that to identify the rate at which reactions occur, you need to understand a few things. 1. What rate of reactions means. 2. What happens in a reaction as particles collide in what we call collision theory. 3. Understand the particles' distribution as the reactions occur using Boltzmann distribution. And that 4. Activation energy is essential.